All right, so the last lecture you guys saw a bunch of syn and anti-dihydroxylation reactions and then ozonolysis reactions. Those are pretty unique in terms of the addition reactions. The last one is a very common addition reaction, but it's also unique. And this is called catalytic hydrogenation. And it's very straightforward. If you've got an alkene, let's say cyclohexene, you treat this with hydrogen gas, and then a catalyst, oftentimes it's platinum or palladium, and oftentimes these are embedded on carbon, so it's not just elemental palladium. That would be very expensive. If you treat this, you can add hydrogens across a double bond, and they end up getting added in a syn orientation. This is really useful for changing an alkene into an alkane. In fact, this will even work with alkynes. You can take an alkyne, which is a triple bond, and reduce it all the way to an alkane as well, and we'll see that next chapter. Some of you are probably familiar with this reaction in your kitchen. So I'll draw a molecule out here. They're both wedges for the hydrogen, showing that they're both syn to one another. So let's say I've got a fatty acid like this. This is a cis fatty acid, right? Most natural fatty acids are cis, they're not trans. And most of these are found in vegetable oils, right? So most vegetable oils contain these cis fatty acids in them. If you take this and treat it with hydrogen and some sort of catalyst like palladium on carbon, you can actually reduce this double bond. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And you can go all the way to the alkane. The neat thing with this, right, is a vegetable oil is normally a solid or a liquid. Normally a liquid, with some exceptions. When you hydrogenate it, all of a sudden you can convert this to a solid. If you've ever used Crisco, you're pretty familiar with this, right? So vegetable oil that's hydrogenated is oftentimes branded as Crisco or that hydrogenated vegetable oil. What's the problem with using those vegetable oils, though? Does anybody know from a nutrition point of view? Trans fats, right? Oftentimes, this actually interconverts the cis alkene to a trans alkene on accident because they don't fully hydrogenate it, they only partially hydrogenate it. And that results in these trans fatty acids that are quite unhealthy and lead to a lot of heart problems. More and more, to avoid that, what they do is they end up substituting in coconut oil and palm oil because those are solid vegetable oils in order to get the desired consistency that they want. But it is an important chemistry reaction in food science.
PDC?
That's palladium on carbon. So what it is when you actually scoop it out of the jar, it just looks like graphite powder, but it actually has a trace amount of palladium on there. Palladium and platinum are very, very expensive, and so they try to embed it on a surface to get the most out of it. The nice thing with it, too, is it's catalytic, and so you don't have to use very much of it at all. So let's take a look at some of these reactions. We're not going to get into the mechanism because it involves a lot of surface chemistry, but I did want to differentiate a couple different types of hydrogenation reactions. The first one is the one we've already seen, where again we've got palladium on carbon. And when we do this, we only get one product. We know it's going to be the syn product. So in this case, we would have both methyl groups coming off the same plane. Do we have to worry about an enantiomer here? Why not? It's an identical compound. So what do we call this type of compound where it has stereocenters, but it's superimposable on its mirror image? It's a meso compound, right? So in this case, we don't have to worry about a mixture of enantiomers, but sometimes we do. And this type of catalyst system is referred to as a heterogeneous catalyst. And what that means is the catalyst doesn't dissolve. This is kind of a neat reaction to do. Essentially what you do is you get this big bottle that's heavy walled. You put your compound in there with a little bit of solvent. You put in a small scoop of palladium and carbon. You end up attaching it to this hydrogen tank, and it puts it in something that looks like a paint can shaker, and it actually shakes it up. The whole point is to increase the surface area of your solution and expose it to the catalyst and expose it to the gas to get it to dissolve into the solution. The neat thing with this is you can actually see the pressure drop as the hydrogen gas gets absorbed, and you can add more pressure as needed. So it's a really straightforward old reaction. However, it is getting kind of dated, and it isn't used in cases where you're worried about preferentially making one enantiomer over the other. And so I'll show you the newer examples. Oop. So I'll call this example number 2. And for these newer examples, we'll take, let's say, this compound right here. I'm going to treat this again with hydrogen gas, but this time instead of using a heterogeneous, excuse me, instead of using a heterogeneous catalyst, we're going to use a homogeneous catalyst. I can't talk today. I might have to edit that out on the video.
You at least have water here.
I do have some water up here. I might have to get a drink in a second. All right, so just like we saw before, we'll get 2 different products. One, for example, will have both of the hydrogens as dashes, which means that methyl group will be a wedge. And then the second one, we can imagine, will have both of the methyl groups, both of the hydrogens as wedges, which means the methyl group in this case will be a dash. What's the relationship between these?
Diastereomers.
They're diastereomers, right? These are easy to separate, right? They have different physical properties. You can distill them. You can isolate them using chromatography and separate them that way. However, quite often chemists want to avoid that. And so what they use are special catalysts, and we'll talk about that in a second. But this catalyst is unique compared to palladium and platinum. This actually does dissolve. So this is homogeneous. Where it does dissolve. So this has a rhodium center with ligands around it. It has 3 triphenylphosphine ligands and 1 chlorine ligand. The cool thing with this is you can swap out one of these ligands for a chiral ligand, and when you do that, the hydrogens prefer to attach to one face of the alkene over the other, and you can actually preferentially make one enantiomer or one diastereomer over the other. So we'll write that down. Can use a chiral ligand to favor one stereoisomer. This is a really common catalyst. This is referred to as the Wilkinson's catalyst. That's the generic one that I have shown here. And it's been used for quite a while, and it's used a lot in inorganic chemistry as well. So if you go on in chemistry, you'll see it over and over again.
A catalyst that does dissolve or doesn't dissolve? What do you mean by that?
So a homogeneous means it does dissolve in the solution. So when you mix it up, you don't see particles floating around, right?
Yeah.
So the heterogeneous catalyst, that palladium on carbon actually stays suspended the whole time in solution. It looks like a milky black solution. And so it doesn't dissolve in solution. And so we classify that as a different type of catalyst. Yep. So let's make a small note of this where RH, Cl, PPH3 is the Wilkinson's catalyst. The only reason I tell you guys this full name is occasionally in different textbooks or even on the ACS exam, You might just see it written out as Wilkinson's catalyst, and people will say, well, what the heck is that? It's just another catalyst that's used for hydrogenation reactions. Does that make sense? All right, this chapter is pretty dense, so at the end of the chapter, I'd like to do a concept review where we kind of link everything back together. And the first thing I'd like to focus on is the Regio Chemistry of the various reactions we've learned. And really what I mean by this is whether or not the reaction is Markovnikov or anti-Markovnikov. And I'm just going to abbreviate it. So let's take a really simple example. We've got our alkene, and we're going to do addition of, I'll say, blue H and red A. It could be any two, or I shouldn't say any two. It's always going to be a hydrogen, and then A can be anything else. So let's draw out both options. We've got one where A adds the more substituted carbon, one where A adds the less substituted. Which one's Markovnikov? Will it be the one on the left or the right?
Left.
Left, right? So this would be Markovnikov. This would be anti-Markovnikov. All right, let's think about it this way, right? What about if we use HBr? Will that be Markovnikov or anti-Markovnikov? Markovnikov. So this was our hydrohalogenation, excuse me. And I'll just put in the reagents here. That was the one with HBr. What if we want the bromine to add anti-Markovnikov? With peroxide. So I'll say HBr with peroxides. So we can control which position the bromine adds on pretty easily. All right, what if we want an alcohol to add Markovnikov? What reagent should we use? Give you a hint. It's pretty similar to HBr. What's that? Not quite. So alcohol, right? So imagine the A is an OH there. What would we want to use?
Water.
Water and a strong acid, right? So this would be acid catalyzed hydration. And we said that's when you have catalytic H plus with water. All right, what if we want the alcohol to go anti-Markovnikov? That's when we use hydroboration oxidation, right? So let's make a list of what that is. We said step 1 is BH3 THF. And then step 2 was peroxides and sodium hydroxide. And if you remember the trick I told you guys, I said anytime you see peroxides, that's a big clue that it's going to be anti-Markovnikov, right? All right, so we've got two different ways of controlling that. We also have one additional way of controlling hydration. What's the one we use when we want to avoid rearrangement and we want Markovnikov hydration? Yeah. And that one's also pretty straightforward. Excuse me. That's when we use mercuric acetate and water in step 1. And who remembers what we use in step 2? Yeah, sodium borohydride. So this, I think, kind of exhausts the ones where we have control over Markovnikov versus anti-Markovnikov. But I always like to kind of organize things into charts like this as a way of keeping track of everything. All right, so that tells you which carbon things get attached onto. But additionally, we need to pay attention to whether or not things are going to be syn or anti to one another. So let's make a list of that. And that falls under stereochemistry. So syn versus anti addition. So just like before, I'll get a nice little chart going. So I'll do addition of X as blue and Y as red. And we know syn addition is when they're both coming off the same face. So you could have X and Y. And then in addition to that, you could have one where they're on opposite faces, and I'll say X and Y. And because we are creating new stereocenters, we do have to pay attention to enantiomer, so I'll write plus EN for each of these. So you could end up with both of these. The one on the left we know is syn. The one on the right is anti. And these do get pretty complicated to keep track of. So I'll get us started with this. We've got syn dihydroxylation. All right, if we want two alcohols pointing off the same face, what reagent should we use? It was one of the ones from the video. What?
KMNO4.
Yeah, potassium permanganate. So KMNO4. Sodium hydroxide. And you have to be very, very careful to run this cold, otherwise you can over-oxidize it. That was one option. The other one was osmium tetroxide, followed by sodium bisulfate and water. Or you can use NMO or another reagent to make the osmium tetroxide catalytic, but our book doesn't get into it too heavily. Osmium tetroxide is pretty nasty stuff. It can make you go blind, so you have to be very careful with it. In either case, though, these will install two alcohols syn to one another. What if we want two alcohols that are anti? Does anybody remember what reagents we need if we want anti-diols, or anti-alcohols, I should say?
NCP.
Yeah, MCPBA. So step one was MCPBA. Does anybody remember what that stands for? Meta-chloroperoxybenzoic acid. That's some good bar trivia right there. Step two is treat this with dilute acid. That will give you the anti-diol. So we can now control diol formation, whether or not it's syn or anti. All right. What about with halogenation? Let's say I throw in Br2. Will that be syn or anti? Anti. So I'll put halogenation here. So something like Br2. Why is it that it's anti? Does anybody remember? Yeah, the bromonium ion, right? So it forms that three-membered ring, which means it has to do a backside attack. It can't do a front side attack. We always end up with the anti-addition product with halogenation. All right, what about with hydroboration oxidation? That was one we previously covered up here. We said hydroboration oxidation is anti-Markovnikov, but we also know whether or not it's syn or anti. Who remembers?
Syn.
It's syn. And so we'll clarify this. Hydroboration, oxidation. And let's make a note. It's syn with respect to the hydrogen. Some students get really confused with this. If you think back to the pod, right? Let's pull up the pod even. In the pod, if you look at that last step, we did hydroboration oxidation, but can you see how the alcohol is on the same face as the hydrogen? That means it was a syn addition and the alcohol is installed in the anti-Markovnikov orientation. All right, so let's go back and add that in. We've got hydroboration oxidation. I won't add the reagents in since we have it up above. And then what about hydrogenation? What if we're adding H2? Is that syn or anti?
That's also syn.
Syn, okay. And we said that's when you have hydrogen gas and something like palladium on carbon. All right, what about the halohydrin reaction? Let's say we want to install a bromine and an alcohol.
You mean water?
Yeah, so bromine and an alcohol, so one would be the X position, one would be the Y position. Would that be syn or anti?
Anti.
It'd be anti. It's really similar to the halogenation reaction, but water outcompetes bromide. So this would be our halohydrin reaction. And that's when we have Br2 and water. Does that make sense? I know it's a lot to remember, but do your best to retain this information. All right, there's one last thing that will come in handy, especially as the year goes on, and this is ring opening. All right, we saw a few examples where we have some sort of three-membered ring, right? So let's say we've got Z with a positive charge. Z is just a placeholder element right now. And we know that Z can be bromine when it's in a three-membered ring. It can be a chlorine. It can be an alcohol. It can be mercury with an acetate group coming off. It can be a lot of different things, right? But we've seen in most of these that some sort of weak nucleophile can actually attack in. However, it usually prefers to attack the more substituted carbon and ring open it, right? So the nucleophile prefers to attack the more substituted position if Z has a positive charge. And like I said in the video, this has to do with bond strengths, right? So this bond right here, thought I had my highlighter on. This bond right here is weak, and that has to do with the fact that that carbon that the arrow is attacking is more stabilized going through a polarized transition state, and it's easier to actually break that carbon to Z bond. So it is a little bit weird to think about, but it's due to the electronics, not the sterics. Sterically, you'd say, shouldn't the nucleophile have a harder time attacking? Yeah, that's half the story, but electronics actually dominate, and we know that based on the products that we observe. Yep.
So it's the you got sewing material, you had the wedges and dashes on the bottom side, but then you flipped it to the top on the product. Is that because of the fact that the nucleophile is attacking on the bottom side?
Yeah, so that's a good question. So let's say we've got A and B, right? This would still be A and B right here. Just like an SN2 attack, you're kind of flipping the umbrella inside out. We're not changing the wedges to dashes, it's just inverting, essentially. So does that make sense?
Yeah.
Okay. All right. So one thing I really like to do at the end of every chapter is to look at the summary of reactions at the end of the chapter. It looks very overwhelming, because it is. But what I've done is I've tried to identify the mechanisms I really want you to know. So in this case, the blue circled mechanisms are the ones I want you to know from start to finish, right? So let's say hydrohalogenation, that's reaction 1 up here. That's something like HBr adding to a pi bond. That's a pretty straightforward reaction, right? Reaction number 3, where we have hydronium, right? That's pretty easy to do as well, so I want you to show that mechanism. Addition of bromine across pi bonds, I want you to know. The halohydrin reaction, where you have water and bromine, I want you to know. The addition of acid to epoxides, I want you to know, so that's the one over here. I don't expect you to show formation of the epoxide. That gets kind of steppy and confuses students, so you can ignore that. But really, it's just those main 5 reactions. Believe it or not, I'm trying to trim things down to the most essential elements here. So try to focus on understanding those, but know the reaction outcomes for all of these. A good way of getting good at these is to look at a fill-in-the-blank study guide. So take that same study guide, black out all of the reagents, and see if you can fill them in. Do this over and over and over and over again until it becomes second nature to you. In addition, if you go on my website, you'll see flashcards listed for each chapter. You can do that, print them off, cut them into individual rows, fold back the product side, or blank out one section of it, and you can quiz yourself. So a lot of my students last year did that. Sometimes it works even better if you just make your own flashcards and add to it as the term goes on, because the process of writing it out helps you retain a lot more as well. So there is a lot going on in this chapter. We do have our first quiz tomorrow, so make sure that you do study tonight. Try to study with a friend if you can, so that you can catch each other's mistakes as well. What we're going to do at the last part of the class period, though, is I've got a small activity for you guys. These are problems I really like from the textbook. So the first one has a starting material, a bunch of different reactions based on that starting material, and then it wants you to fill in the question marks. And then the back page is a little bit different, where it gives you the starting material and product, and then wants you to fill in the reagents necessary. So this is a really good way of studying for the quiz tomorrow. Try to do this backwards and forwards a few different times if you can, until you feel absolutely confident on it. So I'll let you guys work in small groups, but try to do this without notes as much as possible. I know it's very tempting just to flip through your notes as you work on these.